Earlier in this lecture, we talked about Galois groups of cubic polynomials. And now we're going to adapt these ideas to deal with the more complicated but similar case of Galois groups of polynomials of degree 4. Okay, so let's suppose that our polynomial f of x is given by x to the fourth plus ax cubed plus bx squared plus cx plus d. So just like an important first step with cubic polynomials was to make a change of variables to change our polynomial x cubed plus ax squared plus bx plus c to one in which the x squared coefficient was 0 that had the same Galois group, we're going to do something really similar here. We let x equal y minus a over 4, and you can compute that f of x equals g of y equals y to the fourth plus py squared plus qy plus r, where what's the difference is now the cube coefficient is 0. So this is a simpler polynomial. You can solve for what p, q, and r need to be in terms of a, b, c, and d. You get these complicated looking expressions. Okay, so this is not something I would expect you to memorize for an exam, like what p, q, and r are in terms of these original coefficients, but you should know this idea of making a change of variable so that you get a quartic whose cube coefficient is 0. And what's the point of doing this? It's the same as what we said for cubics, since the roots of f of x and g of y only differ by an element a over 4 that is in f. F of x and g of y have the same splitting field over f. So by definition, they have the same Galois group. And that's the thing that we're trying to figure out. And also, since every root is being translated by the same element in f, the discriminant is defined as a product over differences of roots squared. So f of x and g of y have the same discriminant as well. Okay, so now we can compute the Galois group of f by computing the Galois group of g. But how do you do that? So we divide this into cases. First, what happens if g of y is reducible? Well, if it factors as a linear polynomial times a cubic polynomial, where maybe the cubic is irreducible, maybe it's not, we see that the Galois, since the linear polynomial is x minus something that's in f, adjoining that root to f doesn't get you anything new. So the splitting field of g of y over f is the splitting field of this cubic factor over f. So the Galois group of g, which is the Galois group of f, is the Galois group of this cubic factor. And what is the Galois group of this cubic factor? That's something that we analyzed in detail earlier in this lecture. Okay, so now we understand what happens when g has a linear factor. If it's reducible and it doesn't have a linear factor, then it has to factor as a product of two irreducible quadratic polynomials. And okay, we know the roots of a quadratic polynomial. We know how to describe the splitting field of a quadratic polynomial. So the splitting field of this product of two irreducible quadratic polynomials is the field generated over f by square root of d1 and square root of d2, where d1 and d2 are the discriminants of these quadratic polynomials. Let me just say we've let x equal y minus a over 4. Here we're talking about the discriminant of a quadratic polynomial in terms of, we're writing square root of d1, where d1 is the discriminant of a quadratic polynomial. This is just a good opportunity to remind you that we have assumed that the characteristic of f is not 2. Okay, so what is this splitting field? If d1 and d2 differ by a square in f, meaning that their ratio is a square in f, then square root of d2 is in the field generated over f by the square root of d1. So the splitting field, f adjoins square root of d1 and square root of d2, is just f adjoins square root of d1. So in this case, the Galois group of f is the Galois group of f adjoins square root of d1 over f, which is a quadratic extension of a field of characteristic not equal to 2, so it's isomorphic to z mod 2z. So what's the other case? It's when d1 and d2 do not differ by a square in f, meaning that their ratio does not differ by a square in f. Then f adjoint square root of d1 square root of d2 is a biquadratic extension. So this is something that's already come up in our discussion of examples of field extensions so far. And we know that in this case, the Galois group of f is isomorphic to z mod 2z cross z mod 2z. Okay, so that completely takes care of the case where a quartic polynomial is reducible. So I'll pause and erase and talk about the more challenging case of how to understand the Galois group in the case that g of y is irreducible. Let's consider the more difficult case where our quartic polynomial g of y is irreducible. So what do we know? We know that the Galois group of this irreducible quartic is isomorphic to a transitive subgroup of S4. S4 is a finite group, so we can just get in there and see what are all of these transitive subgroups. And a little group theory exercise shows that there are only a few possibilities. You could have the Galois group being S4, or it could be A4, or it could be a CeLO 2 subgroup of S4. So what do these look like? They're all isomorphic to the dihedral group with 8 elements, D8. They're not normal in S4. There are 3 isomorphic conjugate subgroups. Okay, you could have the Galois group being isomorphic to z mod 2z cross z mod 2z, which, how does that show up inside of S4? Think of the group of 4 permutations, the identity 1, 2 times 3, 4, 1, 3 times 2, 4, and then 1, 4 times 2, 3. So you can see that this is a transitive subgroup of S4. For any element I in S4, there's some element in here, sigma, so that sigma of I equals j, where j is any other element of S4. Okay, and then z mod 4z, also a transitive subgroup of S4. How does this show up? It's a subgroup, take the subgroup generated by any 4 cycle. So such a subgroup is not normal. There are 3 isomorphic conjugate subgroups. I should say this one, this z mod 2z cross z mod 2z, this is normal. Remember that a subgroup in Sn is normal if and only if it's the union of conjugacy classes in Sn. So this is the trivial permutation together with the conjugacy class consisting of permutations with cycle type 2, 2. Okay, so if we have our irreducible quartic, we know the Galois group is isomorphic to one of these 5 possibilities. How do we know which case we're in? And there's one big idea that you should remember, which is associated to each irreducible quartic polynomial g of y, there is another related polynomial called the resolvent cubic. Okay, we're going to describe the resolvent cubic in terms of its roots. So let's name the roots of g of y, alpha 1, alpha 2, alpha 3, alpha 4. And we're going to consider these functions of these roots. So theta 1 will be alpha 1 plus alpha 2 times alpha 3 plus alpha 4. Theta 2 will be alpha 1 plus alpha 3 times theta 2 plus theta 4. And alpha 3 will be alpha 2 is alpha 1 plus alpha 3 times alpha 2 plus alpha 4. And theta 3 is alpha 1 plus alpha 4 times alpha 2 plus alpha 3. So you can see how each one of these thetas is a product of alpha I plus alpha j times alpha k plus alpha l. All right, so it's clear that alpha 1, alpha 2, and theta 1, theta 2, and theta 3 are in the splitting field of g of y over f. If you have some field that contains each of these roots, alpha 1, alpha 2, alpha 3, alpha 4, it definitely contains each of these theta 1, theta 2, theta 3. And what happens when you permute the alphas is you also permute theta 1, theta 2, and theta 3. Okay, so using this observation, you can consider the polynomial in x whose roots are theta 1, theta 2, and theta 3. And you can see how to express the coefficients of this polynomial in terms of the coefficients of the polynomial g of y. So you can see the details of this calculation in Dummett and Foote, but the idea is, what is the x squared coefficient of this polynomial? It's negative the sum of these thetas, and you can compute the sum of these thetas in terms of these alphas. Okay, so what does this show? We take this cubic polynomial h of x, whose roots are theta 1, theta 2, and theta 3, and you can write it in terms of the coefficients of g of y. This is x cubed minus 2px squared plus p squared minus 4r times x plus q squared. And this polynomial is the resolvent cubic for g of y. So, if I'm being really honest, I do not expect you to memorize what the coefficients of the resolvent cubic are in terms of the coefficients of g of y. It is good for you to read through this argument in Dummett and Foote and make sure that you understand that you can express the coefficients of the resolvent cubic in terms of the coefficients of g of y. But what's more important is I want you to understand the idea behind where the resolvent cubic comes from and what its roots are in terms of the roots of this original polynomial g. Okay, so what does this polynomial tell you about the Galois group of g? I'll pause and erase and say a little bit more about how they're related. What does the resolvent cubic for g of y tell you about g of y? Well, one thing that you can check is you can compute the discriminant of the resolvent cubic, and you can compute the discriminant of this quartic g of y, and you can see that they're the same. And one of the things that was true that we said earlier about g of y and this polynomial f of x that we started with is they have the same discriminant as well. So you can compute the discriminant of the resolvent cubic by you can compute the discriminant of the quartic by computing the discriminant of the resolvent cubic. And okay, you can do this in terms of the coefficients of the resolvent cubic. And what you get is some big expression that I've written here. You can see the details in Dummett and Foote. The point is not so much what exactly this discriminant is, but the fact that you can compute it given this cubic in terms of these original coefficients, p, q, and r, that, remember, came from the original coefficients of the quartic a, b, c, and d. So given this formula, you can then give the formula for d in terms of a, b, c, and d. So I super do not expect you to memorize this formula for an exam, but this is useful if you want to do like explicit computations, working it out with the formula in front of you. You can write down the discriminant of any quartic polynomial in this way. Okay, so what does the resolvent cubic tell you about the quartic? Well, the roots of the resolvent cubic are in the splitting field of the quartic. So that means that the splitting field of the resolvent cubic doesn't have to be the splitting field of the quartic, but it is a subfield of the splitting field of the quartic. And if you take the splitting field of the quartic, that's a Galois extension, and now you have a subfield that you know something about. And what this tells you, using the fundamental theorem of Galois theory, is that the Galois group of the resolvent cubic is a quotient of the Galois group of the quartic. So this can be a really useful idea in determining possibilities for the Galois group of the quartic. Because if you compute what the resolvent cubic is, you compute its Galois group, maybe it's big, maybe it's something like S3, then you know that the Galois group of the quartic needs to contain, it needs to be a group that's big enough to have a quotient that's isomorphic to S3. Okay, so I'll pause and erase. And then I'll describe to you this recipe for I give you a quartic polynomial, an irreducible quartic polynomial now. We've already understood the reducible case, but I give you an irreducible quartic polynomial, and you tell me what is its Galois group. Let's describe how to compute the Galois group of an irreducible quartic. We're going to understand different cases based on the resolvent cubic. So the first case we'll consider is when the resolvent cubic h of x is irreducible in f bracket x. We'll further divide into two cases. First, if d is not a square in f, by which I mean, what is d? It's the discriminant of a polynomial. Which one? H of x and g of y, and even this original quartic polynomial f, all have the same discriminant. So d is just the discriminant of the resolvent cubic and also the discriminant of this quartic g of y. So if d is not a square in f, what does that mean? That means the Galois group of f is not contained in A4. This is something we proved in the last lecture. Same thing, but now applied to the resolvent cubic. The Galois group of h is not contained in A3, so it's isomorphic to S3. Okay, so we have the Galois group of f is some transitive subgroup. Well, okay, so first let me say the Galois group of h is isomorphic to S3, and this Galois group is a quotient of the Galois group of f. So that means the degree of the splitting field of g of y is divisible by 6. So what do we know about the Galois group of f is it's a transitive subgroup of S4 that's not contained in A4, and its order is divisible by 6. And there's only one possibility now. The Galois group has to be all of S4. If you just look at the possibilities that we had before, we had two groups of order 4, a group of order 8. Neither one of those is divisible by 6. A4 has order 12. That's divisible by 6, but we know the Galois group is not contained in A4. So we're just down to this one possibility where the Galois group is all of S4. Okay, so what if D is a square in F? That means the Galois group of F is contained in S4 in A4. Applying the same observation about D being a square in F to the Galois group of H says that the Galois group of H is isomorphic to A3. So what does that mean? Well, this is the quotient of the Galois group of F, and this means that the splitting field of g of y has a subfield of order 3 over f. So the degree of the splitting field of g of y is divisible by 3. So what do we need? We need a transitive subgroup of S4 that's contained in A4 that has order divisible by 3. And what are the possibilities? There's only one possibility left. The Galois group of F needs to be isomorphic to all of A4. Okay, so that completes the description of the Galois group of an irreducible quartic in the case that the resolvent cubic is irreducible. So now let's think about the case where the resolvent cubic is reducible. If h of x splits completely in f bracket x, what does that mean? Well, we know its roots are theta 1, theta 2, theta 3. So that means that each of theta 1, theta 2, and theta 3 are in f. So what does that mean? Every element of the Galois group of f fixes theta 1, fixes theta 2, and fixes theta 3. They're all in the fixed field of the full Galois group. Okay, so what are we looking for? The Galois group of f you can think of as a set of permutations in S4 that permute the roots alpha 1, alpha 2, alpha 3, and alpha 4. So you can check which subgroup of those permutations fix theta 1, which remember was defined as alpha 1 plus alpha 2 times alpha 3 plus alpha 4. So we can see that the stabilizer of one of these theta i's is isomorphic to D8. And the stabilizer of all three of them, if you fix theta 1, fix theta 2, and fix theta 3, you get an intersection of those three subgroups. And the subgroup of S4 stabilizing each of these theta i's is this subgroup of size 4, the identity 1, 2 times 3, 4, 1, 3 times 2, 4, 1, 4 times 2, 3. So what do we know? we know that if everything in the Galois group fixes theta 1, fixes theta 2, and fixes theta 3, everything in the Galois group is contained in this subgroup. This subgroup has size 4. And the Galois group of an irreducible quartic has to be order at least 4, because you adjoin one root. The splitting field has to have degree at least 4. You adjoin one root, and you get a degree 4 extension of F. So what does that mean? That means the Galois group has to be contained in this subgroup of size 4, and it has to have size at least 4, so it has to be this subgroup. So the Galois group of F in this case is isomorphic to Z mod 2Z cross Z mod 2Z. It is this subgroup of permutations. We're down to one final case. So if the resolvent cubic is reducible but doesn't factor as a product of 3 linear factors, it has to factor as a linear polynomial times an irreducible quadratic polynomial. That means that one of these theta i's is in F and the other 2 are not. So exactly one of theta 1, theta 2, and theta 3 is in F. Let's say it's theta 1. We can rename our 4 roots alpha 1, alpha 2, alpha 3, alpha 4 to make it theta 1. Okay, so what does that mean? The Galois group of F stabilizes theta 1 because it has to fix everything in F, and theta 1 is in F. But it does not stabilize theta 2 or theta 3. Okay, so looking at our possibilities for our transitive subgroups of S4, we can see that we're down to 2 possible Galois groups. The Galois group could be, it has to be contained. The stabilizer of theta 1 is isomorphic to D8. So that means that because the Galois group stabilizes theta 1, it has to be a subgroup of this copy of D8 inside of S4. It could be all of D8, or it could be isomorphic to Z mod 4Z, to the cyclic subgroup of size 4 inside of D8. And how do we know which case we're in? This is actually a little tricky. You can see the details of the very, very end of this argument in Dummett and Foote. But what I'll say is, you know that you have F adjoin square root of D as a subfield of the splitting field of this polynomial. So if you take this quartic G of Y that is irreducible in F bracket X, and now you factor it instead in F adjoin square root of D bracket X and check whether it's irreducible or reducible, that's enough to tell you which of these 2 cases you're in. Okay, so what have we done? So in the last lecture, we talked about how to tell whether the Galois group of a polynomial, so take a polynomial f of degree n, it permutes, the Galois group of that polynomial permutes the n roots of that polynomial. And we talked about how to tell, so we know that the Galois group is isomorphic to a subgroup of Sn. We talked about how to tell whether that subgroup is actually contained in An. Then we looked at f of small degree. We saw what happens when f is a quadratic polynomial. We saw what happens when f is a cubic polynomial. And one big idea was the discriminant of the polynomial plays an important role. And then this thing that we've been talking about in this video is adapting that argument for cubics to the case of quartic polynomials, where first you do some change of variables to get rid of one of the coefficients. Then you can understand what happens in the case that your quartic is reducible. A next really big idea is to study the resolvent cubic of this quartic polynomial. And then, knowing the set of transitive subgroups of S4, using information about the resolvent cubic, we can determine the Galois group of the quartic in every possible case.